Our next subject is examining types of chemical reactions. This information is very useful for predicting products of a reaction. You are given the reactants, and then you should be able to predict the products of the reaction if it fits into one of the 5 reaction types that are listed here on the board. Note that these types or categories of chemical reactions are not a complete exhaustive list, but many reactions that we encounter in introductory chemistry classes falls into one of these 5 categories. You need to be able to be familiar with these categories, know them, and use the information presented here to be able to predict products of reactions. Notice this information in Chem 2A is found in section 7.2, and in Chem 22 it is found in section 7.6, 7.8, and especially clearly organized in section 7.10. Okay, the 5 types of chemical reactions that you are responsible for knowing. Number 1, synthesis or combination reaction. Either term is fine. I'm giving you a general format for what this category of reaction looks like, so it sort of helps you organize in your mind the difference between each type. In a synthesis or combination reaction, you have 2 different reactants, usually 2 different reactants, either elements or compounds, and they react to form one single product that clearly would have to contain all of the elements found in the reactants. So A plus B, element or compound, either one, and reacting to give you a single product that must be a compound. So let's take a look at a couple of examples of single replacement reactions. The first one, a gas phase reaction between nitrogen, a diatomic element, and hydrogen, another diatomic element. They combine, they react together to produce one single product, ammonia. And balancing the equation, as we just looked at and learned in the previous video, you would need a coefficient 1 in front of the nitrogen, 3 in front of the hydrogen, and of course producing ammonia with a coefficient of 2 in front of the ammonia. Taking a look at the second equation, we see here that ammonia gas reacting with HCl gas, so in this instance both of the reactants are compounds, producing one single new compound, ammonium chloride, an ionic compound. All ionic compounds are solid at room temperature, and we indicate that with the S. Right, so synthesis combination reactions, you make a single product. In decomposition reactions, it's sort of like the opposite with respect to the fact that now you only have one single reactant. So if you're looking at a situation where there is only one reactant showing to the left of the arrow, it must be a decomposition reaction. And that single reactant, which is a compound, can decompose to produce at least 2 products, either elements or compounds. So let's take a look at a couple of examples of decomposition reactions. The first involves a carbonate compound, calcium carbonate, an ionic compound, solid at room temperature. When you heat it, and that's what this little triangle means, this process involves heating. Calcium carbonate will decompose to produce calcium oxide, another ionic compound, and carbon dioxide gas. And just making a little note here about the carbon dioxide gas, right? Carbonate compounds will always decompose to produce carbon dioxide gas. You always get CO2 gas produced whenever you do a decomposition of a carbonate compound. So that idea is important to remember. You will always make CO2 gas as a product whenever you decompose by heating a carbonate compound, an ionic compound containing the carbonate ion. Let's take a look at our second example. involving the ionic compound, and hopefully you can look at this formula, use your nomenclature skills, and see that this is the ionic compound potassium chlorate. When potassium chlorate decomposes, you produce potassium chloride, another ionic compound, as well as oxygen gas. And again, this reaction will happen upon heating, so putting the triangle there, and notice I've written in a different color above the arrow a formula of another substance. This substance is manganese 4 oxide, and I'm telling you that manganese 4 oxide is a catalyst. Now, what is a catalyst? A catalyst is not a reactant, nor is it a product, so you would never write it on either side of the arrow. It's always written above the arrow, and its formula is never involved in the balancing process for the reaction. It itself is not undergoing a chemical change. Its role is to speed up the reaction. So that's the function of catalysts. If something is acting as a catalyst, it's acting to speed up the rate of the reaction without itself undergoing any permanent change. So it is neither a reactant nor a product in the equation and not used for balancing. So manganese 4 oxide is the catalyst for this reaction, and whenever you decompose chlorate compounds, you always produce oxygen gas as a product when you decompose chlorate compounds. The next category of reactions we're going to look at is single replacement, or you could call it displacement reactions. So single replacement reactions, alternate name, single displacement reactions. They have this general format where one reactant is an element, the other reactant is a compound, and the element displaces, in this instance, the positive part of the compound. So A comes and displaces B, and now B as a product will be in its elemental state, and you now have a new compound with A as the more positive part and C, of course, remaining as the negative or more negative part of the compound. So A is neutral as an element, as all elements are, but then it ends up in this positive state. B is positive, but then changes or is converted into its neutral elemental state, and C remains negative in both the reactant and product. So examples of single replacement or displacement reactions following the arrow up here to the top of the board on the right hand side. I provide you 2 examples of single replacement reactions. The first involves magnesium, a metal in the solid state, reacting with hydrochloric acid in solution. The magnesium comes and replaces the hydrogen in HCl, and so now you have hydrogen converted to its elemental state. Magnesium, which was neutral, is now a +2 ion in combination with a -1 charge on chloride. So chloride is not changing charge here. The reaction really is a replacement of the magnesium with the hydrogen, which is partially charged in the HCl to produce elemental hydrogen and magnesium chloride. And I speak of hydrogen being partially charged. Technically, this is a partial positive charge, but for simplicity's sake, we just talk about hydrogen being positively charged here. So hydrogen becomes an element with a neutral charge, and magnesium is now a part of the compound as the +2 ion. Here is the second example of a single replacement reaction, this time involving zinc metal, the solid, reacting with copper 2 chloride in solution. The zinc is an element with no charge. In the reaction, the zinc replaces the copper 2 ion in the compound. Now copper is in the elemental state with neutral charge, and the zinc is now the +2 ion. Chloride is not undergoing any net change in this reaction and remains as a -1 anion. Okay, let's turn our attention now to the fourth category of types of chemical reactions, and this is the double replacement or double displacement reaction. In this overall general format, you have two different compounds reacting, and they switch cations, so to speak. So like two dancers dancing, and they switch partners. A comes over, replaces C, and pairs up with D to make a new compound AD, and C replaces A to form a new compound, to form a new compound, and let's switch that order here. I see I don't have the positive and negative parts right, to form a new compound, CB. So in this instance, the B's are partial negative and remain partial negative. The B's and the D's remain in their partial negative state, and they just switch their positive cation counterparts. So the B and D remain as negative ions, and they just switch their positive partners, and we now have A paired with D and C paired with B. Let's take a look at two major examples of double replacement reactions. The first is an acid-base neutralization reaction, where you take an acid, react it with a base, and again, we're going to see this switching of the cations in the compounds, so that sodium is now paired with chloride to form sodium chloride, salt. But notice in this instance, when I say salt, what I'm really referring to is any ionic compound other than an acid or a base. So when you do an acid-base neutralization, you switch cations, you come up with a new ionic compound, which we call a salt, and your other product, when the hydrogen ions pair with hydroxide ions, you will make water. And notice I've written water in an unusual formula or format. It's not its typical presentation, HOH, emphasizing that hydrogen ions from the acid combined with hydroxide ions from the base to make water, HOH, and of course you recognize it in its standard chemical format, H2O. Emphasizing also before I leave here, we've talked about acids and how to name them, but you recognize something as a base because it contains the hydroxide ion. So as soon as you see the hydroxide ion in the formula, you know you are looking at a base. So HCl, hydrochloric acid, reacting with sodium hydroxide, the base, to produce sodium chloride, a salt, and water. You always see salt and water produced in the reaction of an acid and a base. Second category of double replacement reactions is called precipitation reactions, and we can abbreviate precipitate as a PPT because we don't like to keep writing that long word out all the time. So precipitation reactions, a second type of double replacement reaction. A reminder about what a precipitate is. A precipitate is a water insoluble compound formed when you mix two solutions together. So the example that I'm using here is a solution which contains iron 3 chloride, and you mix that solution with a second solution containing the salt, the ionic compound potassium phosphate. So two different salts, they're soluble in water, iron 3 chloride and potassium phosphate, each in separate water solutions. When you mix those two solutions together, the solution mixture that is produced will immediately become cloudy and opaque. You will no longer be able to see light through it. It will not be transparent because you are producing an insoluble salt, which we call the precipitate, and that precipitate is iron 3 phosphate. Notice that this reaction occurs because iron 3 comes and replaces potassium in the potassium phosphate compound. Iron 3 ions pair with phosphate to form the precipitate iron 3 phosphate. And the potassium ions that are displaced or replaced take the place of iron 3 ions and pair with chloride to form your second product, the soluble salt, potassium chloride. Let's take a look at our fifth and last category. This is combustion reactions. Combustion reactions always involve oxygen gas as a reactant. The general format for combustion reactions, and this is assuming that we're looking at carbon-based fuels or organic compounds, carbon-based fuels. And we know when we drive our car that the car won't run unless we regularly fill it up with gasoline, a carbon-based fuel mixture with the general formula of compounds containing both carbon and hydrogen in various ratios depending on the specific compound. So methane, for example, CH4, fits into this first category of CXHY. It's a hydrocarbon containing only carbon and hydrogen. Other types of carbon fuels contain not only carbon and hydrogen, but also oxygen. Alcohol compounds, for instance, like ethanol or pentanol, will be in this category of carbon-based fuels containing carbon and hydrogen and oxygen in some specific defined ratio for that substance. If it is a combustion reaction, the other reactant is always oxygen in the air, and you produce as your products always carbon dioxide and water if the fuel fits into one of these general formula categories. And I should also add here, you will make energy as another product. It's not matter-based, but it is the reason why we do combustion reactions, because we want to release the energy, the reactions. Combustion reactions are exothermic. We want to release that energy and do something useful with it, like propel our cars down the road, or heat our houses, or provide the energy necessary for manufacturing, etc., or generate electricity. Note the examples here that are provided below. One involves a reaction that we've done several times in the lab. This is the combustion of methane gas. Methane reacting with oxygen to produce CO2 and water. And balancing the equation, we need a coefficient 2 in front of the oxygen and a coefficient 2 in front of the water product. And again, we recognize that we are also going to be producing energy in this reaction, which we use in the laboratory when we light a Bunsen burner to heat and provide the heat necessary for a reaction or some other process we're doing in the lab. The second reaction that I'm giving you is the reaction of the alcohol pentanol, We looked at both of these reactions when we examined the process of writing and balancing chemical equations. Pentanol reacting with oxygen to produce carbon dioxide and water with coefficients in the balanced equation of 2, 15, 10, and 12. So summarizing again, these are the 5 types of chemical reactions that you need to know and use this information to predict products of reactions for synthesis or combination, decomposition, single replacement / displacement, double replacement / displacement, and then lastly, 5th and last, combustion reactions.